let's take a look at this gate. So we've got two NOR gates that have been cross-connected. Now we don't need to worry about them being OR gates because what's inside this blue box here we consider to be a single gate. So we've connected two NOR gates together to build a new type of gate. And this new type of gate is an SR flip-flop, sometimes also called an RS flip-flop, same thing. So just consider what's in the blue box as being a single gate. It's got two inputs on the left, here and here, and one output on the right, here. And the output is just wired across to a resistor and an LED, and that means when the output's on, we'll see the LED lit. The two inputs, set and reset, are connected via switches back to 5 volts, so we can close the switch in order to put a 1 into the set or a 1 into the reset. We also have a set of graphs at the bottom. So the top graph is looking at the set input, and you'll see that when I move the cursor onto the top graph that the set lights up blue. The middle graph is looking at the reset input, and the bottom graph is looking at the output. You can also go the other way and highlight, if we highlight the wire going into the set input, you'll see at the top graph turns blue, and on the reset, the middle graph. So that's how you know which part of the circuit the graph relates to. And this is really the equivalent of an oscilloscope trace. So I'm going to start up my circuit, and the graph here will start running left to right, and we'll see how the circuit behaves. So at the moment we've got a 0 going into set and reset. Neither of the switches is closed, and the output is off. So at the moment on our truth table here, I could make a copy of that 0 and put it there, and 2 zeros in gives us 0 out. Switch open, 0, 0 in, 0 out. So let's see what happens when we close the S, the set input. I can just click on this switch to close it. It turns green, showing that it's on, and you can see that the output is on. So I'll just complete the next part of my truth table here and say that if the reset is off and the set is on, then the output is on. Reset off, set on, and you can see here that the output is on. So that looks good so far. The only problem is if I now go and turn off this set input, the output has stayed on. Now that might be what some of you predicted, that this is effectively a turn on switch and this is effectively a turn off switch. But that gives us a little bit of a problem, because what do we put in our truth table? Now both inputs are off and yet the output is on. So this top line is no longer true. So with this sort of gate, a flip-flop gate, the standard truth table doesn't really work, because the output of the flip-flop depends on not only the two inputs, but the state that the output was on at the time when the inputs changed. Now, on the one hand, this sounds confusing because we had been using truth tables to describe how our gates operate, and now that seems to have broken down a little bit. But on the other hand, it's quite easy to understand how this works. We momentarily press the set button to turn it on, and then we momentarily press the reset button to turn it off. So essentially what we really have is something that behaves like a regular start-stop button on an electrical machine. You can push in the green button here to start, but you don't need to hold the button in. You let go of it again and the machine stays on. You press momentarily the stop button to stop it, but again, you don't need to hold it in. And you can see that's how our circuit's behaving. Press the set button, which is really the on or start button. The output comes on, release it again, and the output stays on. So the output latches on, and same with the off button, the reset. Pressing that and letting go again knocks the output off and it stays off. And we can see the states of the inputs and the state of the output on these graphs down below. So if we look at this input, which is the top graph, closing the switch, if you look over here at the right, turns it on. So up is on, down is off. So if I open and close this set switch, you'll see that the graph goes up, down, down. So up is on or 1 and down is off or 0. If I do the same with the reset, it's the middle graph, on, off, on, off. And on the bottom graph, we have the output itself. So if you look back here, top left, and I press the set button and release it, we should find that the output here has come on. And sure enough, we can see it here on as time goes past. And then if I hit the off button just momentarily, it is now switched off again. The gates that we looked at before, and, or, not, NAND, NOR, these are known as combinational logic gates or logic circuits that they build. This type of gate, a flip-flop, is known as sequential logic.